Calibration of volumetric glassware, section 2.9. Calibration is so important. This is what we're going to be doing in experiment 1. It's important to know how accurate our glassware is, and everyone's glassware will be slightly different, so we want to make sure everything is on par. So all instruments have a scale of some sort of measured a quantity, such as mass, volume, force, or electric current. Calibration is the process of measuring the actual quantity that corresponds to an indicated quantity on the scale of the instrument. For instance, if you have a 10 milliliter volumetric pipette and you calibrate it and you figure out that it actually only measures 9.98 milliliters every time you use it, even when it's hitting the meniscus, then at least we know accurately that every time we add it, we're not actually adding 10 milliliters, we're adding 9.98. So we need to calibrate it to make sure we're 100% sure of the amount of volume we are adding. So manufacturers certify that the indicated quantity lies within a certain tolerance. So typically that volumetric pipette will say it's 10 milliliters plus or minus 0.02. So they're saying that every time you measure a volume with that pipette, it's going to give you a volume of 9.98 to 10.02 milliliters. And it's going to be somewhere in there, which is great. So you'll be calibrating your glassware to kind of figure out what range you are measuring. And as long as that, your desired amount is in that range, then it is good. The bigger this number, the less accurate and precise it is. Volumetric glassware is going to be the best options, but just note that graduated and so on and so forth, these numbers will get bigger. So yeah, we want to use volumetric. If you're very lucky, you might know your specific pipette has very, very small numbers. Like for instance, it delivers 10.016 plus or minus a very small number like this. That means that it's very, very accurate and very precise. This tells you precision. For greatest accuracy, we calibrate volumetric glassware to measure volumes associated with a particular piece of equipment. So each individual pipette, each volumetric flask, and things like that. Thermal expansion. In most careful work, it is necessary to account for thermal expansion of the solution and glassware with changed temperature. So we have to kind of account for that. If I have a density at one temperature, it'll be different at a different temperature. So there is an equation. This is the correlation for thermal expansion. So C represents concentration, D represents density. So I like to say this is a prime. It's an apostrophe, but I'll say C prime, or these primes are at one temperature and then the other ones at a different temperature. Just make sure you're consistent and don't flip-flop the temperatures. Here is a very helpful graph that you will be needing for experiment 1. So at different temperatures, you'll notice that, ideally we always assume the density of water is 1 gram per milliliter, but look at how it's changing. As temperature is increasing, the density is slightly decreasing. However, it's definitely roundable to 1. We have to take that into account when we do math with external expansion. So if you have to incorporate density, you could use that, or if you have to go from grams to milliliters or milliliters to gram, you could also use the volume of 1 gram, and that's going to be important too. So I'll show you when to use each. For this table, it's just at higher temperatures. So you'll notice, we have a different density and volume for every single temperature. Let's practice. This is the effect of temperature on solution concentration. So a 0.03146 molar aqueous solution was prepared in winter when the lab temperature was 17 degrees Celsius. What is the molarity of the solution on a warm day when the temperature is 25 degrees Celsius? So we have the C prime over D prime equals C over D. We know that C prime equals, and it doesn't really matter as long as you're consistent. I can say this is C or C prime. 0.03146 molar. And then D, I will have to go back to that table And if I go to the table and find 17 degrees Celsius, I find the density is 0.998777 grams per milliliter. Do not round. Every number on that table is significant. The second one at 25 degrees Celsius, we don't know the concentration, but I do know what the density is, and that's 0.997047 grams per milliliter. So once you have all of that, you can plug it in. And rearrange using algebra to solve for C. And while the number is not really that different, so 0.03146 versus 0.03141, this does prove that at different temperatures there are slightly different, concentrations due to the density changing. So if you need to, use this equation, make sure you know you're plugging in the right number, solve for what's missing. Here's another example. An empty weighing bottle has a mass of 10.313 grams. After the addition of water from a 25 milliliter pipette, the mass was 35.225 grams. If the lab temperature is 27 degrees Celsius, find the volume of water delivered by the pipette. So first, I know my empty weighing bottle and then my bottle with my water. I have to subtract them to find just the volume of the water, or the mass of the water. So mass of water is 24.912 grams. Don't round. Wait till the very end to round if you have to, but just don't round too soon. From the table, if I was to find 27 degrees Celsius, I can't use density here. I have to actually use the volume value, the other numbers. So at 27 degrees Celsius for 1 gram of water, the volume is 1.0046 milliliters. So I'm going to take my starting number, 24.912 grams of H2O, and I'm going to kind of use my equivalent that I just created. 1.0046 milliliters divided by 1 gram. That way my grams cancel. And I have 25.0265 milliliters. The last practice question of the chapter says the mass of water delivered from a 50 milliliter pipette is 49.891 grams. If the lab temperature is 19 degrees Celsius, find the volume of water delivered by the pipette. And then it gives us an equivalence. It says that 1 gram of water at 19 degrees is 1.0026 milliliters. So remember that you can make the equivalence like this. 1 gram equals 1.0026 milliliters. And then if you start with what you're given, 49.891 grams, and use that equivalent to convert it to a volume, it would look something like this. That way, your grams will cancel, and you're going to be left with milliliters. All right, next up, plug it into your calculator. So that'll be 49.891 multiplied by 1.0026, and then divided by 1. That is 50.021. So the answer will be number 2.